The wheels just retracted. This train is now floating. Nobody builds trains like this. 603 kilometers hour. The fastest thing ever built that runs on the ground. Japan has been building this for 60 years. Most people have never heard of it. 86% of this railway goes through solid mountain. There was no other way. Started at $9 billion, now $72 billion. Still climbing, still being built. They drilled 246 kilometers of tunnel through the hardest mountains in Japan. The geology collapsed. The schedule collapsed. The cost exploded. They kept going. Colder than outer space. This is what makes the train float. One governor, one signature. He stopped the $72 billion project for 4 years. This is how Japan built the fastest thing on land, and why it nearly never happened. 1964, Japan launched the bullet train. It changed the world. Then Japan asked, what's next? The Tokyo Shinkansen is full. 12 trains per hour. No more capacity. Japan needed a bypass. The coastal route curves around the mountains. The Maglev cuts straight through them. Research began in 1962. It took 63 years to turn those equations into a railway. 1977, the first test track, 7 kilometers in Miyazaki. The first levitation, the first proof it worked. Miyazaki proved it. Levitation worked. Superconducting magnets held. The next step, the Alps. 1990, geological surveys began in the Alps. 19 years of surveys before a single tunnel was approved. The geology under the Southern Alps is 300 million years old, and unlike engineers had tunneled through before, 1,400 m of overburden, fault zones. Underground rivers, rock pressure that crushes steel. May 27, 2011. After 49 years of research, Japan approved the Chuin-Kanansen. Construction could begin. The Yamanashi test track came first. 18.4 kilometers of real Maglev railway built to prove everything. New Austrian tunneling method. Drill, blast, shot, rock bolt, repeat. 11 kilometers of test tunnel drilled. 6 hours per blast cycle. Drill, blast, muck, show treat, rock bolt. 6 hours every day. A pilot tunnel drilled first, sampling the rock before the main machine commits to it. The guideway must be accurate to millimeters over kilom. Laser checked every single section. Figure 8 coils embedded in both walls. Levitation, guidance, propulsion, all in one coil design. The motor isn't in the train. It's in the track. 18 kilometers of electric motor embedded in concrete. 18 kilometers of cable runs, every coil powered, every sensor connected before a single train runs. The propulsion system needs variable frequency power. A dedicated substation built just to supply it. The control center monitors every coil, every sensor, every millimeter of train position simultaneously. The first test train arrived in 1995. No wheels visible, no panogram roof, a capsule designed to float. No wheels touching the track, no overhead wire for power. Everything about this train breaks every rule of railway engineering. First levitation, 1997. The tires retracted. The train rose 10 centimeters. Floating on invisible force. December 1997, 531 km/h, a new world record. On their very first full-speed test, 200,000 people rode the test train before a single commercial passenger boarded. Japan tested everything. October 2014, ground broken on the real line. 286 kilometers, the biggest railway project in history. Shinagawa to Nagoya, 286 kilometers, 246 kilometers of that inside tunnels. The new station goes under the existing bullet train station. Construction without stopping the trains above. Diaphragm walls, first continuous concrete retaining walls built before any excavation begins inside. 40 m deep beneath a live railway station in central Tokyo without a single delay above. The TBM is assembled underground. Too large to be lowered whole, piece by piece in the launch shaft, 14 m wide, 150 m long, for 1,000 tons, 80 tungsten carbide disc cutters on the face. The machine advances 15 m per day through urban ground. Above it, homes, shops, people who feel nothing. One concrete ring installed every 90 minutes. 6 segments per ring. 600 rings per kilometer. Excavated soil travels 5 kilometers on conveyor to the surface. Then trucks, then disposal never stops. Urban soil becomes alpine rock. The TBM slows. Disc cutters wear every 50 m. They must be replaced. Replacing cutters requires entering the pressurized chamber at the tunnel face. One of the most dangerous jobs in construction. A pilot tunnel drilled 1,000 m ahead, reading the geology before the main machine arrives. 1,000 m boring surveys ahead of the face. Japan invented this technique for this tunnel. The geology failed. Schist rock 300 million years old, fractured, unpredictable, unlike any model. Emergency redesign. An ATM replacing TBM in the worst sections. 5-year delay announced. An ATM in the Alps. Slower, costlier, but the only method the geology would accept. 1,400 m of mountain above. Rock pressure crushing the tunnel like a vice. Engineers designed for it. Where rock pressure peaked. Steel arch ribs installed. Then shotcrete. Then rock bolts. Then more shotcrete. Underground rivers encountered at depth, grouted shut, drained away. The mountain fought back constantly. 3 different tunnel boring methods used in one project. An ATM, TBM shield, and conventional drill. Construction without stopping the trains above. Diaphragm walls, first continuous concrete retaining walls built before any excavation begins inside. 40 m deep beneath a live railway station in central Tokyo without a single delay above. The TBM is assembled underground. Too large to be lowered whole, piece by piece in the launch shaft. 14 m wide, 150 m long, for 1,000 tons, 80 tungsten carbide disc cutters on the face. The machine advances 15 m per day through urban ground. Above it, homes, shops, people who feel nothing. 1 concrete ring installed every 90 minutes. 6 segments per ring. 600 rings per kilometer. Excavated soil travels 5 kilometers on conveyor to the surface. Then trucks, then disposal never stops. Urban soil becomes alpine rock. The TBM slows. Disc cutters wear every 50 m. They must be replaced. Replacing cutters requires entering the pressurized chamber at the tunnel face. One of the most dangerous jobs in construction. A pilot tunnel drilled 1,000 m ahead, reading the geology before the main machine arrives. 1,000 m boring surveys ahead of the face. Japan invented this technique for this tunnel. The geology failed. Schist rock 300 million years old, fractured, unpredictable, unlike any model. Emergency redesign. An ATM replacing TBM in the worst sections. 5-year delay announced. An ATM in the Alps. Slower, costlier, but the only method the geology would accept. 1,400 m of mountain above. Rock pressure crushing the tunnel like a vice. Engineers designed for it. Where rock pressure peaked. Steel arch ribs installed. Then shotcrete. Then rock bolts. Then more shotcrete. Underground rivers encountered at depth, grouted shut, drained away. The mountain fought back constantly. 3 different tunnel boring methods used in one project. An ATM, TBM shield, and conventional drill. Blast. The geology forced every change. 10,000 L per minute pumped from the Southern Alps tunnel. Every minute of construction, excavated alpine rock crushed on site, reused as concrete aggregate in the tunnel lining itself. In situ concrete lining poured behind the excavation. Each 12 m pour section takes 3 days. 400 m vertical shafts sunk through the mountain for ventilation and emergency access. 60 separate construction contracts, all running simultaneously. One project, 60 different sites. Underground stations carved from solid rock. The Khufu cavern, bigger than most surface stations. No columns support the station roof. Rock anchors drilled 20 m into the mountain do the work. A complete railway station built inside a rock cavity. 40 m underground with no natural light. Tunnel complete. Now the hardest part. The guideway must be installed to millimeter accuracy over kiln. Every guideway section laser surveyed. Tolerance 1 millimeter over 50 m, 0 exceptions. These recesses in the wall to me. Each one holds a coil. The train floats by interacting with coils. It never touches. That's the engineering. 580,000 individual coils installed in the guideway walls. Everyone positioned by hand. The engine is in the ground, not the train. 246 kilometers of electric motor embedded in concrete. The nose is 15 m long, shaped in a wind tunnel for 3 years, designed to enter a tunnel at 500 kilometers/hour. Tunnel entry at 500 km/h creates a pressure wave. The nose shape took 3 years of wind tunnel testing to solve. Nobium titanium wire thinner than a hair wound 50,000 times per coil in a vacuum environment. The cryostat is a thermos flask the size of a car. It keeps the magnet 4 degrees above absolute zero. Liquid helium loaded at -269 degrees colder than the surface of Pluto. The magnet becomes superconducting. 32 superconducting magnets per train. Each one must be installed, cooled, and verified before the next. Below 160 km/h, rubber tires. Above 160 km/h, the tires retract. The train floats automatically. Entering a tunnel at 500 km/h compresses the air violently. The cabin pressure system prevents ear damage. Inside, it looks like any other train. The engineering that makes it extraordinary is completely hidden. 1,200 sensors per train. Every system monitored, every anomaly reported in real time to the control center. First test, walking pace, every sensor verified, every system checked before speed is applied. 160 km/h tires retract. The train rises. Engineers at the control center watching the levitation sensors confirm. Each test faster than the last. 200, 300, 400, 500. The data confirming what the physics promised. A magnet quenched at 400 km/h. The safety system activated. The train stopped safely. Engineers redesigned the magnet mounting. Track vibration caused the quench. Engineers redesigned the mounting. Tested again. No quench. Problem solved. Earthquake simulation at 500 km/h. The U-shaped guideway physically prevents derailment. The train cannot leave the track. Every test run generates more data than a moon landing. They've run 2 million test miles. Nothing is left to chance. 2 trains passing at 1,026 km/h combined. The air between them compressed. April 21st, 2015. 603 km/h, a world record. The fastest land vehicle in human history. Inside at 603 km/h, almost no vibration. The passengers could read a newspaper. That is the engineering. At 500 km/h, the Maglev uses half the energy of an equivalent airplane flight per passenger seat. 2013 test track extended to 42.8 kilometers. Full commercial speed testing over longer distances begins. 2,000 kilometers per day, every day. Since 2013, the most tested railway system ever built. The maintenance depot covers 30 hectares. Every train returns here nightly for inspection. A helium recovery plant inside the depot. Evaporated helium recaptured, requified, reused. 8.9 kilometers through Shizuoka. The governor said no. 620,000 people's water supply was the reason. Engineers designed a system to return every liter of groundwater captured during tunneling back to the river. 2027 became 2034, then 2035. Every year of delay, billions more in cost. $9 billion became $72 billion. The geology, the delays, the redesigns, all multiplying the cost. April 2024, the governor resigned. JR Central stock rose immediately. The market knew what it meant. The new governor approved the survey within weeks. After 4 years, construction could resume. October 2024, first boring survey equipment entered Shizuoka. For years of delay, finally over. The Nankai Trough megaquake could strike any year. The Maglev route is designed to survive it. Seismic sensors every kilometer. Trains stopped automatically before earthquake waves reach the track. Japan has a severe construction labor shortage. Some tunnel sections ran at 60% crew capacity. 30,000 construction workers across 60 sites. Most will never ride the train they built. In GU, groundwater levels dropped near the tunnel. Engineers immediately modified the lining to seal it. The 14% above ground uses elevated viaduct, concrete piers, precast beams, the guideway carried on bridges. Above ground or underground. Same tolerance 1 mm over 50 m. No exceptions. At 500 km/h, noise barriers reduce trackside levels to below 70 dB. Quieter than a busy road. A train just passed at 500 km/h overhead. I felt the air move. I heard almost nothing. The noise barriers work. China unveiled a 600 km/h maglev in Japan invented this technology. Now it risks losing the race to open first. 2025, a new improved car introduced. Lighter, cheaper, more efficient. Improving while still building. 2025, 60% of tunneling complete. Shizuoka boring survey approved. Target commercial operation. 246 kilometers of tunnel. 60 construction sites. 30,000 workers still building every single day. Everything built so far is waiting for the train that will make Tokyo and Nagoya 40 minutes apart. Tokyo to Nagoya, 40 minutes through A.